Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this module discusses pulse shaping for digital communications. So in an earlier module, we saw how the shape of the pulse used by a communication system essentially is what completely determines the shape of the communication signal in the frequency domain, or the spectrum of the communication signal. So we learned that, but we did not discuss what type of pulse shapes are generally used in a communication system and what type of pulse shapes are desirable. And this is important because in earlier modules we did in earlier modules when we introduced things like modulation, we tend to use simple pulse shapes like a square pulse or a triangle pulse that are where the entire energy of the pulse is completely confined to within the symbol time from 0 to t. However, most actual communication systems don't use these kinds of pulses. They tend to have very poor spectral properties, and in fact, most systems use pulse shapes that stretch quite far outside of the actual 0 to t symbol time. Now, this means that pulses do overlap, and so one of the first things we're going to discuss in this module is how it's possible to have overlapping pulses and still not suffer from intersymbol interference. The first step in our discussion is to take a slightly different perspective when looking at the modulator in a digital communication system. And so we start by writing an equation for the analog signal transmitted by the communication system, S, and we're going to use the same kind of notation that we used in the signal spectrum module, where we talk about where we represent S as basically a pulse train, a series of delayed pulses, F, multiplied by some signal vector value, S of n, where the signal vector value contains the information content of the signal, and F is just the pulse shape. Now, it's useful for us in this module to think of the transmitter as a filter. And so we can think of the transmitter containing a filter with an impulse response that's basically equal to the basis function. And so that's the filter that I've drawn here. And we often refer to this as the pulse shaping filter. And so in this particular example, we're using a triangular pulse. And so the response of the pulse shaping filter is triangular, and it's been normalized to have unit energy. Now, we want to transmit triangular pulses with an amplitude of plus or minus 2. Now, in order to get a signal to produce its impulse response at its output, we have to feed an impulse into the input of the filter. And so at the output of the filter, we can see our transmitted information sequence is a positive triangular pulse, a negative triangular pulse, and then a positive triangular pulse. And in order to produce this transmitted pulse train waveform, what we do at the input is we pass in a series of impulses. The first one, and each impulse has a weight equal to the signal vector value. And again, remember these are weights and not amplitudes, because these are ideal delta functions where that have 0 width, infinite height, and an area of 1. But in this case, we scale the area so that the area of the impulse is equal to the signal vector value. And so our first impulse at time 0 has an area of 2 multiplied by root t over 3, When this impulse travels through the filter, we produce the first pulse at the filter output. The second impulse occurs at time t. It has a weight of -2 root t over 3, and it produces a negative pulse. And then the final impulse occurs at time 2t and has an area of 2 root t over 3, and that produces the last impulse. And so in this way we can think of the modulator as a filter, which is, as I said, going to be useful in a few slides where we talk about how to produce pulse shapes with both a desirable spectrum and zero intersymbol interference. So in order to look at pulse shape design from a general perspective, what we're going to do next is we're going to look at both the transmitter and the demodulator basically as two cascaded filters. And so we know that the demodulator match filter response is equal to a flipped and shifted version of the basis function. And so what we're going to do is we're going to define a filter response Q that's essentially the convolution of the pulse shaping filter in the transmitter and the match filter in the receiver. And then what we're going to do is we're going to basically look at the system from the output of the sampler at the output of the match filter. And so we're going to sample this cascaded filter response Q at intervals equal to multiples of the symbol time. And so if we take this perspective, then we can think of the output of the system as a series of discrete values, yk, which where yk represents the symbol by symbol samples at the output of the match filter. So y0 would be the first sample at the output of the match filter at time 0. Y1 would be the second sample at the output of the match filter at time t. Y2 would be the third sample at time 2t, and so on. And so what we then have is the output of the match filter is equal to the desired signal component, which is the signal vector value sk multiplied by the filter response qk, a noise component n, and then we have this summation. And remember, I said that in general, most actual communication systems use pulse shapes that stretch well beyond the symbol time, and that means our transmitted pulses are going to overlap with one another. And so this summation represents the overlap from information symbols both before and after our current symbol. And so this is what's known as intersymbol interference, because other symbols are interfering with our current symbol because everything is overlapping. And so what we would like to do is come up with a pulse shape design where we basically get rid of this intersymbol interference component. So as it turns out, there are a number of potential pulse shapes that satisfy our zero intersymbol interference criterion. And what we're going to do then is we're going to start out by defining the zero ISI condition in a very general sense, and then we're going to look at a bunch of examples of pulse shapes that satisfy the zero ISI condition. And in order to do this, we need to review the concept of aliasing. And aliasing is a discrete time signal processing concept that refers to what happens to the spectrum of a signal when you sample an actual continuous time signal and you convert it into a discrete time signal. And so let's start by taking a look at our signal Q of t and taking the Fourier transform of it. So this second line of the equation is just the regular old analog Fourier transform of the signal Q, except that rather than having a continuous time variable, I've just substituted in the discrete time samples. Now, this is an integral from minus infinity to infinity, and this third line in the equation is just a manipulation of the equation so that we can write the integral from minus infinity to infinity in terms of a bounded integration from minus pi over t to pi over t and a infinite summation. So basically what this third equation does is it kind of chops the spectrum into pieces of width 2 pi over t, and then the summation just kind of adds them all up together. Now, the second and third line of these of the equations the second and third line of this equation are completely equivalent to one another. I'm just using this special form to help us with what's going to come next. This next equation is the inverse discrete time Fourier transform of our sampled signal right here. And what I'm going to do in the next line is just perform a variable substitution. So the discrete time frequency, little omega, is equivalent to the continuous time frequency in radians per second, capital omega, multiplied by the sampling time, or equivalently 2 pi f divided by the sampling frequency, because the spectrum of a discrete time signal is confined to be between minus pi to pi. Now, if we then compare this equation to this equation, and note that both are equal to the sampled version of our cascaded filter response, then it means that this discrete time spectrum of the signal is equal to the infinite summation of a bunch of shifted copies of the continuous time spectrum of the signal, which is what we have in this summation, which is the standard result, right? So when you sample a continuous time signal, the discrete time spectrum is a bunch of repeated copies of the continuous time spectrum. And in standard signal processing, what you need to make sure is that the repeated copies of the continuous time spectrum don't overlap. If they do, this is what's known as aliasing. And aliasing can be avoided as long as the sampling is performed at twice the maximum frequency of the continuous time signal being converted to discrete time. And this is what's known as the Nyquist frequency, or the Nyquist sampling frequency. Now, as we said in the previous slide, aliasing is normally avoided by sampling at the Nyquist frequency. However, the matched filter is only sampled at once per symbol. And so that means aliasing at the output of the match filter is unavoidable. So aliasing always occurs at the output of the match filter. Now, normally this would be a bad thing in sort of general signal processing, but it's not a problem for us. Remember The purpose of the communication signal is not to perfectly preserve the received analog signal, but just to extract the information content from it. And as we showed in the demodulator section, or the demodulator module, we can sample once per symbol interval and recover the signal vectors, which contain all of the transmitted information. And so aliasing it definitely occurs and it's not a problem. However, we still are trying to work towards this zero intersymbol interference condition. Now recall that the intersymbol interference term a few slides ago is equal to the summation of k not equal to m s m q k minus m. And so we want this term to be 0. So basically we want q to be equal to 0 for all samples except for when m is equal to k, because that's the desired, or that's our current symbol basically. And so our 0 ISI condition is basically equivalent to trying to set our cascaded filter response equal to the delta function, which, again, is what zero intersymbol interference means. We are not going to avoid intersymbol interference between our actual transmitted information pulses, or our transmitted communication pulses. However, we do want to have zero ISI at the output of our match filter when we're dealing with the cascaded response of both the pulse shaping filter in the transmitter and the match filter in the receiver. And so we're going to set that cascaded filter response to have an impulse response equal to a delta function. And what this basically means is that when you take the Fourier transform of a delta function, you get a constant. And so we want the discrete time spectrum of the signal at the output of the match filter, which is equal to the aliased version of the continuous time spectrum. We want it equal to 1, or equal to a constant, basically. And that basically just means that as long as all the overlapping aliased spectrum or spectra of the pulse that we use, as long as all that aliasing adds up to something that's flat in the frequency domain, we have zero intersymbol interference. And any pulse that satisfies this is what's known as a Nyquist pulse. And as it turns out, there are a number of pulses that satisfy this condition, and we'll go through a few examples. The first pulse is the Sinc pulse. And so in the time domain, we have a Sinc pulse where the zero crossings occur at t, 2t, 3t, and so on. And in the frequency domain, we have the square spectrum of our pulse shape, but then the dotted line represents the aliased spectrum, or spectra. Now you'll notice that in the case of the Sinc pulse, the aliased spectrum to the right of our main spectrum lines up exactly so that we have a nice flat top, and the aliased spectrum down here does the same thing, lines up exactly again, so we have a nice flat constant filter response. Because the aliased spectrum is flat, the inverse Fourier transform of this is a delta function, and we have zero intersymbol interference. The Sinc square pulse is another example. So it has basically the same or a similar shape to the Sinc pulse, but its lobes are a little bit bigger because it's been squared. Again, its zero crossing is at t, 2t, 3t, and so on. In the frequency domain, a Sinc squared pulse has a triangular spectrum, and then the dotted lines represent the alias spectrum. But again, you'll notice that if you add these spectra together, you get a constant, because as the main spectrum is going down, the alias spectrum is coming up, and so the addition of these alias spectra, is a constant. The inverse Fourier transform of this alias spectrum is a delta function, and so if you use a Sinc squared pulse, then you have zero intersymbol interference as well. Another common pulse used by communication systems is what's known as the raised cosine pulse. But before we talk about the raised cosine pulse, it's useful for us to take another sort of perspective looking at the intersymbol interference, or the zero ISI property of the Sinc pulse, by looking at how you would actually construct a Sinc pulse train in the time domain. And so let's say we're implementing a binary PAM system using Sinc pulse shapes. And what I've shown here is the first pulse in that pulse train. So it has an amplitude of +1 at time 0. And you can see kind of its standard Sinc pulse shape. It hits 0 at time 1, 0 at time 2, 0 at time 3, and so on. In this next slide, we've added our second pulse. So our first pulse has an amplitude of 1 at time 0. Our second pulse has an amplitude of -1 at time 1. And these, in this upper plot, the pulses overlap, and I've sort of shown them kind of individually. However, the actual transmitted signal is the summation of these two pulses, and so the bottom plot shows the summation of the two pulses, and you can see, we've got some sort of distortion between our sample times, and that's because these pulses are overlapping with each other. However, if you look at exactly time 0, you'll notice that our amplitude is still exactly equal to 1. And if you look at exactly time 1, you'll notice that our amplitude is still equal to -1. That's because at exactly the symbol times, the value of the interfering pulse always goes to 0. So for example, for our +1 pulse, right at 0, the second interfering pulse has a value of 0. And for our -1 pulse, at a time of 1, the first pulse has exactly a value of 0. So basically what's happening is the value of each transmitted pulse lines up with the zeros of all of the other pulses. And this becomes more clear if we look at a third pulse. So here in this top plot, we have our original +1 pulse, followed by our -1 pulse, and now a +1 pulse. And again, note that the desired value of our transmitted pulses always line up with the 0 values of all of the other interfering pulses. And the actual transmitted signal is the summation of these three. And again, between the symbol sample times, we see some distortion and some unusual values, but at 0, we get exactly 1. At 1, we get exactly -1. And then at 2, we get exactly 1 again. And finally, to conclude the example, here's a fourth pulse. So we're now transmitting 1, -1, 1, and 1. Again, you can see how these are lining up with the 0 points of all of the other interfering pulses. And when you add up these 4 overlapping pulses together, we have 1, -1, 1, and 1. Right? So you can think of these sinc pulses then, as long as we transmit one new sinc pulse at exactly every symbol interval, it's going to line up with the zeros of all the other sinc pulses, and we have 0 ISI, or 0 intersymbol interference. Now, one of the this all works fine as long as we are looking at the symbol values at exactly 0, exactly 1, exactly 2, and exactly 3. So as long as we're sampling at exactly the multiples of the symbol time and our synchronization is perfect, then we have 0 ISI. However, if we, for some reason, don't sample at exactly the symbol intervals, for example, if we sampled here due to some timing or synchronization error, obviously we're going to experience some distortion from the other pulses. And so intersymbol interference does occur if we sample, if we have any kind of timing error, basically, or timing jitter. And this is made worse by the fact that the sinc pulse tends to take a long time to decay, right? So the tails of the sinc pulse, if there's timing error, the tails of a sinc pulse are going to interfere with symbol after symbol after symbol until they decay down small enough that they're not really causing a problem anymore. And unfortunately, the tails of the sinc pulse do not decay very quickly. A solution to this problem is to multiply the sinc pulse by a damping function, and that's what I've drawn here. Here's our original sinc pulse, and here's a damping window, and you can have a number of damping windows. This particular one is shaped like the half cycle of a cosine pulse, hence the name raised cosine pulse. And when you multiply by this damping window, what happens is it attenuates the tails of the sinc function, and you get tails that look like this. So even if there is timing error now, the intersymbol interference is going to be reduced. So here we have the equation for the raised cosine basis function, or the basis function that you use when you're using a raised cosine pulse. Here we have, it basically consists of 3 parts. Here we have our regular old sinc function. This term is that damping window, and this term is the energy normalization function, because the energy of a raised cosine pulse is t multiplied by 1 minus beta divided by 4. And the beta factor is what's known as the excess bandwidth. The spectrum of the raised cosine pulse looks basically, if I just draw the single-sided spectrum, looks basically like this. It's flat up to a point equal to 1 minus beta over 2t. Then it kind of looks like this, and then finally gets down to 0 at a point of 1 plus beta over 2t. The factor beta is known as the excess bandwidth. Now, as you increase beta, the amount of damping increases. So you increase the rate of decay of the tails, which is good from an intersymbol interference perspective if you've got error in your system. So if you have timing error in your system, you want beta to be as high as possible. Generally, beta is greater than 0 and less than or equal to 1, and we express it as a percentage. Of course, the penalty of increasing beta is that it increases the bandwidth occupied by the pulse. So the bandwidth, occupied by a traditional Sinc pulse is 1 over 2t. And as you increase beta, you cause the overall bandwidth of the signal to increase, hence the name excess bandwidth. Now, just to show that the raised cosine pulse is in fact a Nyquist pulse, here is a picture of the raised cosine pulse in the time domain, and here is the aliased raised cosine spectrum in the frequency domain. And you'll see, we have something flat, and then as the spectrum sort of drops off, the aliased copy increases at the same rate, and we have a flat spectrum. So the last point to emphasize about pulse shaping is that understanding the bandwidth of your pulse shape is a very powerful idea because it allows you to link analog channel bandwidth to system throughput. And often a communications engineer will be asked to design a system with a certain throughput, and we'll have to do it over a certain analog channel that has a certain sort of passband characteristic. So it'll pass frequency or a certain range of frequencies, and after that the channel will start to attenuate it. And so the first problem faced by the communication engineer is what kind of modulation scheme you need to use in order to satisfy your throughput. We know as we increase the number of signals in our modulation symbol set, we can transmit more bits per symbol and increase our throughput. However, we don't want to use too many symbols because as our signal vector diagram gets more crowded, the chances of bit error rate increase. And so we want to have just the right number of symbols in our symbol set. And we can calculate this now using our knowledge of pulse shaping. And so this is best illustrated just with a quick example. Let's consider we have a telephone cable with an analog bandwidth of 1 megahertz. And you've been asked to design a PAM communication system with a throughput of 10 megabits per second, and you've determined that you want to use a raised cosine pulse with a 25% excess bandwidth in order to provide a little bit of protection against intersymbol interference. And so the first thing you can do is determine the symbol rate that is allowed by your analog channel. And so if we use W to represent the bandwidth of our channel, and we're assuming basically that our channel has, some sort of low pass filter kind of characteristic where, anything above a bandwidth W of 1 megahertz starts to get attenuated. And so we want our raised cosine spectrum to fit exactly within this 1 megahertz. And so we know the cutoff of our raised cosine spectrum is 1 plus beta over 2t. And if we set that equal to W and solve for 1 over t, which is what we're doing over here, we get a symbol rate of 1.6 megasymbols per second. Now, the next step is we know that our throughput in bits per second is equal to the number of bits per symbol, k, divided by our symbol time. And so what I've done down here is just solve for k, because we know symbol time and we know the data rate that we need. We take the ceiling of it, and we get 7 bits per symbol is how many bits are required. And so the number of PAM symbols in our constellation must be equal to 2 to the 7, or 128.